All right, everybody, we are ready to get started here. Welcome to the Morrison Planetarium. My name is Mary. I'm going to be your presenter today. I'm in the pilot's booth at the top of the room, waving my arms. Hello, everybody. Welcome. And today you are here to see Tour of the Universe, which is one of my favorite shows that we do here in the Morrison Planetarium, because in this show, it is a completely live show where I'm going to be our pilot as we fly around the universe together. So in the next 20-ish minutes, we're going to start out at Earth. We're going to zoom out as far as we can out into space, and we'll come back safely home at the end of the show. But before we can get started on our journey, I do have a few quick planetarium rules I need to go over with everyone. First of all, please no eating or drinking while you're in the planetarium today. While you're following that first rule, the next rule should be pretty easy. Make sure to keep your mask on for the whole show. Even once the lights come down, please keep that mask on. If you have a cell phone, a camera, a tablet, anything like that that could give off light or sound, both of those can be pretty distracting in here, so we want to make sure that those are all put away during the whole show. And for your safety in this dark theater, but also to keep up our distancing guidelines, make sure to stay in your seat until the end of the show and just listen for my instructions at the end for how we'll exit. And last but not least, this can create a very immersive experience. And while I do my best, I'm not a perfect pilot, so if at any point throughout the show you feel any dizziness, any motion sensitivity, just go ahead and close your eyes for a few seconds. And that should help your brain remember you're just sitting in a chair in a planetarium, not actually flying around in space. So without further ado, go ahead and sit back, relax, and we will get started. All right, so we are starting our tour of the universe today relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And it may look a little bit strange and look not too much like home right now, because I was actually watching the International Space Station as we were loading up the show here today, and it slowly was drifting over onto the nighttime side of Earth. So right now below us is the nighttime side of Earth, and I believe we're over the Atlantic Ocean at the moment. We were over the Midwest just a minute ago. And that really does give an idea for how quickly the International Space Station is going around our planet. You can see where it orbits, where it goes around the Earth with this yellow line that I just put up. Only takes them about 90 minutes to orbit us once. And I always start out our tours at the International Space Station because that's how far humans travel out into space right now. And throughout the show, we're going to check in with our human activity out here in space as we go farther and farther away and see how far has our human influence gone. So we'll see things like how far humans have traveled, how far we've sent our spacecraft, how far we've sent any sort of signals out into space, and we are going to travel even farther than all of that. And the way that we can do that in the planetarium today is by using a free planetarium software, actually. I'm using OpenSpace, which is a free and open source planetarium software. So if you have a computer at home, you might be able to download it and fly around the universe yourself. And OpenSpace uses all real, accurate data. So what we're seeing now as I zoomed away is the actual where these clouds and weather patterns were on the Earth earlier this morning. And these images of the Earth were taken by various satellites that we have going around our planet. And it's the exact position of where the International Space Station is right now. So it really is over there, flying above the Atlantic Ocean right now. But that is how far us humans travel right now. You can fit about 6 or so astronauts on the International Space Station at any one time. And people have been living up there for about 20 years, but not the same 6 people. They swap out every few months or so. And the longest that any one particular person has lived up on the ISS is about a year. But I'm not going to stop too long at any one spot throughout our tour today because we have a lot of ground to cover. So I'm going to keep zooming out here, and we're going to change our focus to our closest natural neighbor in space, the moon. Now, when I change focus, it might kind of flip the screen around here quick. So if this makes you dizzy, close your eyes. There we go. And we're going to fly over to the moon. And there's a pretty exciting event that is coming up. I should have double checked the exact date, but if you're here with me in California, we won't be able to see this event happen in California. But if you are really, really far north, or if you're maybe in somewhere in Europe, then you would be able to see an annular eclipse, which is basically a partial solar eclipse where the moon lines up just right to cast a shadow on the Earth. So as I go around to the kind of daytime side of the moon, we're seeing the side of the moon that we never get to see on Earth. This side always faces away from us. But things are lining up right that the moon will cast a shadow on the Earth a little bit in just a few days here. And as we gaze at the far side of the moon, and actually I'll turn off the nighttime side of the moon as we rotate around for a second here, I do want to bring up an idea that I'm going to be using for the rest of the show. So today we're going to be covering some incredible distances. So incredible that it's hard for me to wrap my head around. The moon, for example, the moon is our closest neighbor out here in space, our closest natural neighbor at least. We have some human-made satellites going around the Earth that are closer, but the Earth is our natural satellite close to us. But even though it's the closest object out here in space that we're going to visit, it is still about 250,000 miles away from us, so still quite far away. And as we go farther, we'll see distances of millions or billions or trillions of miles and kilometers. So I'm not going to use miles and kilometers to figure out how far we've gone. Instead, I want us to imagine that we are traveling at the speed of light or faster. So the speed of light is the fastest speed we know of in the universe at all. And if we were traveling at the speed of light, it would take us about 1.5 seconds to get to the moon from Earth. So the moon is a distance of 1.5 light seconds away from us, because that's how long it would take for light to travel there. So roughly the same amount of time that it took us in open space to get to the moon, that's about how long it takes for light to travel to the moon. And when you see the moon in the sky, that's reflected light off of the moon that took 1.5 seconds to get to us. And as we zoom away, I'm going to bring up some more orbit lines, some more lines to show us the paths that things are taking in our solar system. So we'll see some blue ones that show the orbit of the moon and also the orbits of the planets in our solar system. And already as we zoom away, we are traveling much faster than the speed of light using open space, because we're already out to getting to light minutes of distance. For instance, if we focused on the center of our solar system, the closest star to us, the sun that we're seeing to the bottom right there, if we were traveling from Earth to the sun, it would take us about 8.5 minutes if we were traveling at the speed of light. So the sun's about 8.5 light minutes away from us. And there's a couple of different ways we can think about that. One way I like to think of it is that if the sun just disappeared, you wouldn't know about it for 8.5 minutes. But thankfully, there's no reason why the sun would just disappear, so you don't have to worry about that too much. Another way to think about it is that if you walk outside and you look at the sun, first of all, don't do that. Never look at the sun. It's very bad for your eyes. But if you looked at the sun, that's how the sun looked 8.5 minutes ago, not how it looks right now. And within these few light minutes of distance, we've got the smaller, rocky, inner planets in our solar system. So closest to the sun, there's Mercury, and then Venus, and Earth, and Mars. And you may notice there's a pretty sizable gap here in between Mars and the next planet, Jupiter. But that gap is not totally empty space, but it looks like it's totally empty space just because the objects in between Mars and Jupiter aren't giving off, they're not reflecting a lot of light, so we can't really see them. So I'm going to make them really bright so we can see them more easily. And these are the asteroids in the asteroid belt in between Mars and Jupiter. So relatively small rocky objects that we have in our solar system. And not all of the asteroids orbit in the asteroid belt, but the vast majority of them do. So most of the asteroids are in between Mars and Jupiter. But then farther out still, beyond the asteroid belt, we've got Jupiter, Saturn, Uranus, and Neptune. And I'm going to bring up the orbit for my favorite dwarf planet, Pluto. And we're going to spend just a minute over at Pluto. I'm going to fly over to it. Because in open space, we have some really, really amazing high resolution, oops, sorry, that was kind of fast. Some really amazing high resolution images of some of these different locations. So we saw the moon earlier. Those were some images that were taken by satellites that go around the moon. We saw some pretty clouds and stuff on the Earth taken by satellites around us. And we do also have some really nice images of Pluto, because just a few years ago, back in 2015, the New Horizons spacecraft flew past Pluto and took some nice high-resolution images for us. So the side of Pluto I'm going to show you are, these are actual pictures that New Horizons took as it flew by a few years ago. Now, to this day, I often get people asking me about Pluto. So Pluto officially has been called a dwarf planet since the year 2006. But still, working in a planetarium, I frequently get people asking me about Pluto. Things like, what happened to Pluto? Is Pluto still in our solar system? Did it explode? Why do you hate Pluto? And I'm here to tell you, I do not hate Pluto. I really like Pluto. I think it's amazing. Look how pretty it is. It has ice mountains. It has possibly a slushy ocean under the white area we're seeing here. It has nitrogen snow and nitrogen ice. It has an atmosphere with a blue glow that possibly changes as it goes throughout its year. It's a very, very interesting place. But it is still, with all the interesting things it is still officially called a dwarf planet and not a planet like it was before 2006. So why is that? Well, I have to zoom back out to talk about why it is that we don't call Pluto a planet anymore, because it has to do just with what else is around it. So before we saw the asteroid belts, and I was only able to see it because I made all the asteroids much brighter. As I zoom away from Pluto, we can see Pluto's orbit, but then also, let me zoom out a little bit faster. We can see Pluto's orbit, but there are a lot of other things out here by Pluto that are also very dim, so we can't see them too easily right now. And the same was true just in our actual daily lives until the late 90s and early 2000s. We did not have good enough telescopes to see anything this far out in the solar system besides Pluto. But then in the late 90s and early 2000s, we started to see a lot of other objects. And I'm going to show you the paths of these objects next. They're going to pop up rather abruptly, so just a warning. There we go. So we started to find a lot of small objects out here, many of which, if you look at these paths, you can see they kind of go in their own belts, kind of similar to the asteroid belt, but just much farther out in our solar system. So this is what we call the Kuiper Belt, mostly smaller, icy objects, but a few objects that are around the size of Pluto. So as astronomers started to find more and more and more of these little objects out here, they began to question whether or not we should keep calling Pluto a planet or come up with some other category. So back in 2006, it was decided that a planet needs to have cleared its path and have a pretty cleared out orbit. Pluto is inside the Kuiper Belt, and it did not fulfill that requirement, so it was changed to a dwarf planet back in 2006. But if you ask me, that is not a demotion. It's just a reclassification based on other things we found in our solar system. And a couple of the official planets, Uranus and Neptune, we haven't sent any spacecraft by them since the 80s, so Pluto has a one-up on them because New Horizons came by just a few years ago. And speaking of New Horizons, let me show you where that spacecraft is. So I'm bringing up now some paths to show where our farthest spacecraft have gone so far. So earlier, looking at the inner planets in our solar system and traveling from the Earth to the sun, we were talking about distances of light minutes, 8.5 light minutes to travel from Earth to the sun, for example. Out here by Pluto, we're now up to distances of light hours. If we wanted to travel from one side of Pluto's orbit to the other, traveling at the speed of light, would take us about 9 hours. So here we can see just a few spacecraft that we have sent out by Pluto or beyond Pluto, and these have been going for quite a while, depending on which ones we're talking about. So these are showing us Pioneer 10 and 11, Voyager 1 and 2, and New Horizons, which went out to Pluto. And the earliest of these were sent out in the 1970s. So Voyager, for example, Voyager 1 and 2, they've been traveling for about 50 years now. But even so, with these being some of our fastest spacecraft and our farthest spacecraft, none of them have gone as far as light could travel in just a single day at this point. So just around here-ish, we're just getting out to light days of distance. And around here is a little bit of a tricky area of trying to decide, are we still in our solar system or have we left our solar system behind? So we're beyond where the Kuiper Belt is, we're beyond where we've sent our spacecraft, but there's some other things out there, potentially some comets that orbit really, really far away from the sun. The sun has its own gravitational influence that gets weaker but goes out pretty far, has a magnetic field. So it's a little tricky to try to figure out exactly where our solar system ends and where it begins. But right here, you can see the sun has something happening to it. You can see that our solar system is getting kind of bright. And that's because before I was dimming down the brightness of the sun, because if it was its true brightness, we wouldn't have been able to see other things in our solar system very well. So at this point, this is what the sun would look like if you were to fly out into space this far. And right around here is where I like to say, without an argument whatsoever, we're outside of our solar system because we are starting to fly past other stars that are in our galaxy. So checking in real quick about how far we've gone in just the last few seconds here as we've zoomed out in OpenSpace, we are now up to light years of distance. So the spacecraft we have in our solar system have gone a few light hours away. If we were to travel to the closest star to us out here, the closest star outside of our solar system, that would take us about 4 years traveling at the speed of light. So we've jumped up in distance quite quickly as we zoom away. And from here on out, everything we're going to see, this is stuff that is based on what we see in our telescopes and things where we see the light of these objects. It's traveled to us and we look at it here on Earth or with our telescopes that we have around Earth. Because like we saw, we have not sent spacecraft out this far. This is all because of light coming to us and observing it from where we are. But there is one last chance that we have to check in with any of our human influence out here in space. Because if we get to a few tens of light years away, past many of the closest stars to us, I can show you one more thing that we have sent out into space. And that is the radiosphere. So this blue sphere that I've put up here, this grid, is giving us an idea of how far any signals we've sent out could have gone. So we've been sending radio signals that are strong enough to escape our planet since roughly the 1930s, so about 90 years or so. And those radio signals, they are traveling at the speed of light. And as long as they don't run into anything, they're just going to keep on going and keep on traveling out into space at the speed of light, not slowing down. So because of that, the farthest that any of those could have gone by now is about 90 light years in any one direction away from our planet. So that's how far this radiosphere is, 90 light years in any direction away from Earth. But we're going to keep on going. Like I said, we're not going to stop any one place too long because we still have a long ways to go. I'm going to zoom away from the radiosphere, and I am going to keep on the radiosphere because I like to keep an eye on it as we zoom away, see how long you can spot it. And in a moment, our view here is going to shift a little bit. So right now we're seeing mapped out where individual stars are. These are stars that we have mapped out where they are. We know where they are and how far away they are from us. We can see them in the sky as individual dots. But in a second, we're going to transition over to a model of what we think our galaxy would look like if we could go and fly this far out into space. Because again, like we saw, we have not actually flown out this far. Our spacecraft have not gone out this far into space. But we can see lots of things from our view here on Earth of our galaxy. We see gas and dust and stars in our galaxy. And we look at other galaxies and we can kind of try to figure out what our galaxy might look like based on what other galaxies look like. So piecing all of that together, we can make a model like this of what we think the Milky Way galaxy would look like if we could fly outside of it. And it's a pretty flat galaxy. We're in a spiral galaxy, so it's shaped pretty flat like a disk, and it has these spiral arms of gas and dust and stars. In the center, it's quite bright because we have a lot of stars more packed together in the center of our galaxy. At the very, very, very center of that, if you could see it, you would see nothing because we have a supermassive black hole at the center of our galaxy, which is pretty cool. And if we were to travel across our galaxy, traveling at the speed of light, we have once again bumped up into even more incredible distances. If we were to go from one side of the Milky Way disk to the other, traveling at the speed of light, the fastest speed we know of, it would take us about 100,000 years. And if you look carefully, can you still see the radiosphere? The little teeny tiny dot on the right there, about halfway, 2/3 of the way out in our galaxy's disk. But we're going to keep going because our galaxy, the Milky Way, is only one galaxy out here in the universe. As we zoom away, now we're seeing lots of other dots that are going to show up. And these dots, these are no longer individual stars. Every single one of these dots is another galaxy. And every single one of those galaxies has its own billions or trillions of stars. And the colors of the galaxies out here are kind of interesting. These are not the actual colors of these galaxies, though I do think that would be fun if it looked just like cosmic Skittles out there in the universe. But no, we've color-coded these galaxies depending on a variety of things. Sometimes it's color-coded depending on what data set it's part of, so usually what telescope was used to see that particular galaxy and map it out. Or we'll group them together if it's part of a certain group or cluster of galaxies. They're bound together by gravity. So we've color-coded them based on a variety of different factors. And this is a real map. We've mapped out where these galaxies are relative to us. These are galaxies we have seen in our telescopes. But because of that, that means at a certain point, things are going to look a little bit strange. If we zoom out far enough to a few billion light years, we've already bumped up to a few billion light years at this point, you're going to see a strange shape that these galaxies seem to form. It's going to look sort of like a hourglass or a butterfly. Some people say it looks kind of like a pasta or something like that. But the universe is not shaped like a butterfly, unfortunately. I also think that would be fun. But no, this is not the real shape of the universe. This is just because we're looking from our perspective here on Earth. So because we live in a galaxy, that Milky Way galaxy we saw before, and our galaxy has lots of gas and dust and stars and stuff in it, when we try to look in the directions of the gaps we're seeing here on the bottom left and the top right, our galaxy is blocking our view, making it hard to see over in those directions because we just see the stuff that's in our galaxy when we look over in those directions. So there are even more galaxies than this, but this is just the ones that are easier to see and what we've been able to clearly map out so far. And we think there are just as many galaxies over in those gap directions as well. And as we gaze at these galaxies that are incredibly far away, billions of light years away, we're also doing something kind of cool, I think, which is that we're kind of time traveling in a way. Because all this light, it takes so long to travel to us and then get into our telescopes and us to see these places that by the time it does get here, we're seeing these objects how they looked millions or billions of years in the past, not how they look right now. So if you remember at the beginning of the show, I mentioned how if you look at the sun, again, don't do that, don't look at the sun, but if you looked at the sun, that's how the sun looked 8.5 minutes ago. This is what the universe was like billions of years ago. And because of that, that means that there's only so far that I can take you. There's only so far that we can see in our entire universe, and so far back in time that we can see too. And that edge of our, what we call the observable universe, is going to show up all over the place here in just a second, what we call the cosmic microwave background. Now, if you walk outside tonight, and if it's a clear night, and you look up at the sky, you're not going to see this everywhere you look in the sky. Thank goodness. That would scare me. That would be weird. But if you did walk outside, and if you could see microwave light, a lower energy form of light that our eyes can't see, but our telescopes can see, then you would see this every single place you look. And actually, just last week was the anniversary of the discovery of the cosmic microwave background. So back in 1965, a couple of guys out in New Jersey, if I'm remembering correctly, were using their radio telescope and doing some studies. And for a while, were really confused by the cosmic microwave background because it looked just like some sort of strange radio interference that they were seeing. But they did all sorts of different tests and determined that no, this isn't interference from here on Earth. This is something out in space that they were seeing. And this was a big help for the Big Bang theory at the time as well, because before this discovery, it was a little hard to show when or where that might have happened. So the cosmic microwave background, this is a few 100,000 years after when the Big Bang would have occurred, when light was first able to just kind of expand out and go out in all directions. So in simpler terms, I like to think of this as the baby picture of our universe, the youngest light that we can see, and the farthest away that we can see. But since this is the farthest and the youngest, that means I can't take you any farther. So we're going to end our journey today by flying on back home. Now keep in mind, if we were really this far away, and if we were really traveling at the speed of light, this journey home would take us about 13.5 billion years. But thankfully, we're in the planetarium. It should only take us a minute or two. And as we fly back home, I do like to leave folks with one last thought, which is that all of this that we've been looking at, stars, galaxies, cosmic microwave background, planets, dwarf planets, everything we can see, is only a small part of everything we know to be out there in the universe. There's some mysterious things out there, like dark energy. Dark energy is some mysterious force that is causing space itself to accelerate as it expands. There's dark matter, some mysterious substance that we're not quite sure what it is, but we see evidence of it a lot of different places, especially at the edge of galaxies. And we call these things dark energy and dark matter because we're not quite sure what they are, but we do know that they make up about 96% of everything in our universe. So all of this that we've looked at so far is only a very, very small percentage of everything we know to be out there. And that can often make people feel kind of uncomfortable and small, that we're this one tiny dot in this gigantic universe. But while I do agree, makes me feel weird sometimes too, I also like to think of it as, well, yes, we are this one tiny dot, but look at all of this that we have found so far, almost entirely by looking through telescopes. And there's a whole lot more to discover and a whole lot more to learn about. And that's pretty exciting. But even so, every time I give this show, I'm always a little bit relieved when we get back to the radiosphere and we're back in our cozy human realm of the universe. Just have a few tens of light years left to go. And we're going to fly back to the sun, that closest star to us, right at the center of our solar system, past the spacecraft that we have sent out. And we're going to head back to the third planet from the sun, the only place in all of this that we have found life at all so far, which is another pretty incredible thing to think about. And we're back home. Hooray! So with that, I want to thank you all for joining me today for our tour of the universe. I hope you enjoyed flying around in space with me today, and I hope you enjoy the rest of your evening. Thank you all for joining me.